All right, so a little bit more evidence of particle nature of light, and then the official switch or official transfer in our minds here of classical physics to quantum physics. And then we have to look back at that double slit experiment or the single slit experiment for that matter, because there's interference patterns in both. Um, and yeah, we're going to see that that happens with particles. So spoiler alert there. But yeah, so further evidence of particle nature of light, the liberation of an electron and the emergence of a photon, lower energy, and so on, the Compton effect. We're going to look through that one. Basically, it's a really good confirmation of the momentum of light, that light has momentum, which is obviously a particle property. So 1923, fired a beam of high energy X-ray photons, right? High energy light particles, if you will, at a thin metal foil. As a result, he detected emitted electrons as well as emitted X-ray photons that were lower in energy and frequency. As a result, energy and frequency go hand in hand with light, than the photons in the instant light. And so it's what's called the Compton effect. And so the instant photon is acting like a particle that undergoes an elastic. All the measurements show that it undergoes an elastic collision with the metal and emerges as a lower energy. Energy is transferred to other particles. And so yeah, the moment if basically Compton believed that momentum must be conserved and checked into it, and it turned out to basically give us a way of calculating the momentum to do with light. So I got rid of the vectors there, but so momentum equals mass times velocity. But if a photon has no mass, I don't know if you know that or not, but photons don't have mass. How can it have momentum? So we can use Einstein's mass equivalence idea, which we'll see in more detail later on in the course. E equals mc squared, though everybody's kind of familiar with it. So we're just going to use it for now, and you'll see where it comes from later in the course. But mass can be written as energy over the speed of light squared. All right, so momentum is that for a photon, I guess, right? Logically. And so we have this because the speed of light is c. So they write it like this. I'm not a fan of the diagonal slash for fractions. They look pretty and all, but they're not as clear about what is in the top and what's in the bottom. So obviously a little bit easier to read if it's a e over c squared, multiplying a c in the top. C divided by one of those c's is a 1, right? So they cancel out, and you get e over c. Okay, so either way you write it, it means the same thing. It's just maybe a little easier to follow this way. So recall that the energy of a photon is found using E equals h bar f, right? Energy is proportional to the frequency, that h bar constant. The keyboard just doesn't have a bar option for the h. So, and other things here, we've got frequency, v equals f lambda, right? So frequency would solve to be that, and the speed is c. So you put that all together, right? We've got the c over lambda for the frequency. A little off in my arrow description or pointing here. And so energy equals that. And yeah, so we have that multiplication, again, just clear showing of it here. And so that you can tell the C's are going to cancel out, right? So you're just going to get the H in the top and the wavelength in the bottom. Okay, so that's the momentum of a photon. You just do h bar divided by the wavelength of the light. So talking about the momentum of a particle of the light, right? And it equals the h bar constant divided by the wavelength of the wave that is the light. So this equation kind of joins the two together, right? And like it really is like a typical collision, calculate momentum in the x direction and y direction, and so on and so on. So, and if you're getting an electron, it's straight up, normal mass times velocity. The photons, h bar over the wavelength, and it all works. Like we're not doing the heavy math to do with it here, but just suffice to say, if you did get into the heavy math of it, you'd see, and you did, the experiment from scratch yourself, and so on. Every independent scientist in the world has, that has checked into this has confirmed, yeah, like this is just what happens. The Compton effect works. the calculations work out. Momentum shows momentum is conserved, and by definition, then that light has momentum. So yeah, if we were looking at a little bit of calculation to do with this, is what's a photon has an energy of 165 electron volts. What's its momentum? And so first convert to the joules version. We've done that enough before that I'm not going to worry about talking about it a whole lot. But certainly this is this many joules per coulomb, right? So and yeah, we can put in that energy value, and we can put in the h bar constant, and we can solve for the frequency, and then frequency v equals f lambda, right? So speed of light and the frequency, solve for wavelength. Okay, so you get the momentum finally because you have the wavelength, and so you do the h bar divided by that wavelength, and you get the momentum. Okay, so therefore it has momentum, which is mass times velocity, kilogram meter per second, right? So I kept digits all the way through and then round to the 2 significant digits at the end. Just notice on the next page here, that's what you should do, right? Because otherwise here they rounded earlier and ended up with like 9.47. It's a mistake really they've made in that original material that I've adopted from or worked from and modified. Another version here, we have an electron moving at a certain speed, and so what's the wavelength of a photon that has the same momentum as that electron? So basically just calculate the momentum of the electron itself, regular, classical physics, momentum equals mass times velocity stuff, and then this kind of new physics stuff to do with momentum of photons and so on, particle nature of light, just plug the values in, all right, get the wavelength. Okay, so a little bit of calculations. Now, this isn't the main calculation. Obviously, the big calculations that we're not seeing, of course, is all the conservation of momentum stuff. And really, it wouldn't make sense for us to worry too much about that because we're not carrying out the actual experiment, right? So we're just looking at experimental data from the scientific community, or results, I should say, of working with experimental data. And yeah, and that one's done. So this little video here, Compton effect and Compton scattering. Just press pause, I'll get that ready.
Welcome to this video on the Compton effect, where we'll explore the nature of light. The Compton effect, also known as Compton scattering, involves the scattering of high-energy photons by charged particles, usually electrons. When a high-energy photon with a specific wavelength and frequency interacts with an electron, it transfers some of its energy and momentum to the electron. This collision changes the photon's wavelength, frequency, and direction while causing it to lose energy. As a result, the photon's wavelength becomes longer, and this change is referred to as the Compton shift. To understand the Compton effect, we need to consider light as particles known as photons. By analyzing the collision between the electron and the photon as an elastic collision, we can calculate the observed change in the photon's wavelength. The conservation of energy and momentum before and after the collision allows us to establish a relationship for the change in the scattered photon's wavelength. The change in wavelength depends on the scattering angle at which the scattered photon is observed. For small angles, the change in wavelength is relatively small. As the scattering angle increases, the Compton shift also increases. When the scattering angle is 180 degrees, the maximum Compton shift occurs. The Compton effect played a significant role in confirming the particle-like behavior of light and supporting the development of quantum mechanics. It provided experimental evidence that light behaves as particles called photons, contributing to our understanding of the dual nature of matter and radiation. We hope this video has been helpful in shedding light on the Compton effect.
Cool. Note the relation of the scattering angle to the change in wavelength was not something that could be explained based on wave theory. So particle nature of matter was necessary to explain this. obviously, if you go through the details of the, it was a key part of the calculations to do with angular, or it's not angular, but conservation of momentum and energy and so on, right? And photons collide with electrons like particles, transferring energy and momentum. That's a particle analysis, obviously. This interaction causes the photon to lose energy and increase its wavelength. The associated particle calculations make perfect predictions about the resulting form of the light, right? The change in the wavelength. So, yeah, particle analysis working. Notice that this doesn't involve atom energy levels. I said in the previous video that it doesn't involve atoms by accident, but really I misspoke. It just doesn't involve the energy level shifts and so on. So they're certainly not causing the quantization of the photons themselves, right? So further evidence of the particle nature of light is this pair creation thing. So another photon interaction with matter is that when a photon can interact and it can create a pair of particles. So it can disappear completely upon interacting with matter, and so a photon of high energy, like an X-ray photon, comes in and collides with a heavy nucleus, creating an electron and a positron. So a positron is an antiparticle of an electron, and the mass of the products of this interaction is greater than the mass of the original heavy nucleus. So how can particles containing mass result from an annihilation of a particle that does not contain mass? Well, the answer is in that E equals mc squared stuff, right? So the energy of the incoming photon obviously is converted to the mass and energy of the outgoing particles. So again, this interaction, when studied, shows conservation of energy and momentum and so on, as expected with particle interactions. So this pair production simulation, let's grab this quick here. Sorry, let's moved over to my file now. So pair production simulation. Show it quick here. So high X-ray photon coming in, collides with a nucleus, and you get these two pair particles, right? An electron and an anti-electron. So sometimes called a positron, and in the video they called the other one a negatron for some reason, but it's an electron, of course, right? It's just a regular electron. So to do with this interaction, an important thing to know is, of course, that wave theory cannot account for the creating of matter with mass. Right? This requires treating light as a localized packet of energy or a particle called a photon, and then the idea of the energy conversion to the mass equals mc squared kicks in. So yeah. Oh, a note about this: a nucleus must be nearby during the pair production, so it's interacting with this nucleus and making that happen, and that's necessary because the nucleus has to be there to help conserve momentum during the process, right? So which is necessary for particle interactions, right? This conservation of momentum fact being applied to this scenario. So lots of undeniable experimental evidence of particle nature of light. And of course, then there's big consequences to that, right? Like if light is really particles, then how can there be interference patterns, right? That's a wave property. And even more strangeness to come, as I told you before, right? So you'll see that shortly. So, we go back to this interference pattern stuff, and if light's particles, then how can that happen, right? So let's just get this going. There we go. So get my head straight here. I want to go to the red and put a double slit in place, and you send the light towards the double slit, and of course, if it's acting like a wave, it makes perfect sense, right? But then you can move this down to the point where it sends in individual photons, but really, if we're going to send it as electrons, I think that some of them have a way to send one photon at a time. I think you'll see that later. So let's go back to that thing when we get back through this part here, okay? So, this idea of wave and particle duality, or really we're going to call this wave particle duality, right? And so that's coming up in the next lesson more so, but is it a wave or is it a particle? Is what we're looking at. So I'll just read from here again. Everyone knows that water, and hence water waves, are composed of a huge number of water molecules. So is it really surprising that light waves are composed of which are composed of a huge number of particles, namely photons, can have wave properties as well? Well, it is, but the surprise is in the details. You see, more than 300 years ago, Newton proclaimed that light consisted of a stream of particles, so the idea is not exactly new. However, some of Newton's colleagues, most notably Dutch physicist Christian Huygens, you remember the Huygens wavelets, disagreed with him and argued that light was a wave. And so the debate, as we've gone through, raged on, and ultimately experiments carried out by English physicist Thomas Young in the early 1800s showed that Newton was wrong, right? The Young's double slit experiment, wave properties, and so on. However, all right, so the prevailing view of light was subsequently put on mathematically firm foundation by Maxwell. So Maxwell's wave equations, right? Based on wave ideas. So Einstein, however, right? Einstein, the man who brought down Newton's revered theory of gravity, seems now to have resurrected Newton's particle theory of light by his introduction of photons. Of course, we still face the same question. How can a particle perspective account for the interference pattern shown in figure 4.8 down here, right? The interference pattern. At first blush, you might make the following suggestion. Water is composed of H2O molecules, the particles of water. Nevertheless, when a lot of these molecules stream along with one another, they can produce water waves, with the attendant interference properties illustrated in figure 4.7, right? So there's the water waves interference patterns. And so it might seem reasonable to guess that wave properties such as interference patterns can arise from the particle picture of light, provided a huge number of photons, the particles of light, are involved. But it's not really that, right? As in reality, though, the microscopic world is far more subtle and weird. Even if the intensity of light shown in that figure 4.8 is turned down and down and down to finally the point where individual photons are being fired one by one at the barrier, say at a rate of 1 every 10 seconds, so they can't possibly be interacting. The photographic plate will still look like an interference pattern. So long as we wait long enough for a huge number of these separate bundles of light to make it through the slits, and each to be recorded by a single dot at a time as they hit the photographic plate, these dots will build up to form the image of an interference pattern, the image in 4.8. This is astounding. How can individual photon particles that subsequently pass through the screen and separately hit the photographic plate, seconds or hours apart from one another, how can they conspire to produce a bright and dark interference bands of interfering waves? So conventional reasoning tells us that each and every photon passes through either the left slit or the right slit, and we would therefore expect to find the pattern shown in figure 4.6. In other words, just a pattern of, I don't know if I have it here or not, a pattern of just, a blob from going through the one slit. But of course you don't, right? So if you're not bowled over this by this fact of nature, it means that either you've seen it before, or you've become blasé, or the description so far has not been sufficiently vivid. In other words, you just don't quite get it yet. So hopefully you are recognizing that it's weird to see that there's an interference pattern, even though we're sending through particles one by one. But in case it's the latter, let's describe it again, but in a slightly different way. You close off the left slit and fire photons one by one at the barrier. Some get through, some don't. The ones that do create an image on the photographic plate, dot by single dot, and it says, which looks like the figure 4.4. Now, this isn't actually right? There actually still would be an interference pattern. Everybody seems to ignore that, I think, just to not complicate the matter, when you're talking about this. But it's sort of true. If you're just looking at this as the central maximum and you're not noticing the extra stuff, right? So anyways, you then run the experiment again with a new photographic plate. This time you open both slits. Naturally enough, you think that this will only increase the number of photons that pass through the slits in the barrier and hit the photographic plate, therefore exposing the film to more total light than in your first run of the experiment. But you later examine the image produced and you find that not only are there places on the photographic plate that were dark in the first place, in the first experiment, they're now bright as expected, but there are also spots on the photographic plate that were bright in your first experiment but are now dark. By increasing the number of individual photons that hit the photographic plate, you have decreased the brightness in certain areas. Somehow, even though they're temporarily separated, they arrive at very different times, one after the other, individual particle photons are able to cancel each other out and have destructive interference. Think about how crazy this is. The photons that would have passed through the right slit and the and hit the film in one of the dark bands in figure 8 fail to do so when the left slit is open, which is why the band is now a dark area. But how in the world can a tiny bundle of light that passes through one slit be affected by whether or not the other slit is open? As Feynman noted, it's as strange as if you fired a machine gun at the screen, and when both slits are open, independent, separately fired bullets somehow cancel each other out, leaving a pattern of unscathed positions on the target. Positions that are hit when only one slit is open, then aren't hit when two are open. Such experiments show that Einstein's particles of light are quite different from Newton's. Somehow photons, although they are particles, embody wave-like features of light as well. The fact that the energy of these particles is determined by a wave-like feature frequency is the first clue that a strange union is occurring. But the photoelectric effect and the double slit experiment really bring this lesson home. The photoelectric effect shows that light has particle properties as well as Compton scattering and pair production and so on, right? The double slit experiment shows that light manifests the interference patterns properties of waves. Together they show that light has both wave-like properties and particle-like properties. The microscopic world demands that we shed our intuition that something is either a wave or a particle, and embrace the possibility that it is both, or at least at this point that light, shed the intuition that light is either a particle or a wave, and consider the possibility, embrace the possibility that it's both, accept the possibility. It is here that Feynman's pronouncement that nobody understands quantum mechanics comes to the fore. We can utter such words as wave-particle duality. We can translate these words into a mathematical formalism that describes real-world experiments with amazing accuracy, which is what quantum physics is, right? Accept the fact that it's a wave and a particle, and then do the math and calculate and make amazing predictions for decades and decades and decades, which is where we're at. But it's extremely hard to understand at a deep intuitive level this dazzling feature of the microscopic world. So the punchline from all of this debate is, I'll have to put in a slide, but basically, is light a particle or a wave? Here we go. So is light a particle or a wave? Okay. And the answer is yes. It's like my answer when someone asks me if I want apple pie or blueberry pie. It's like, yes. So it's both, right? It has the properties of both. Which is very odd, right? But that's the conclusion of our journey here of looking and seeing about wave particles and particle properties of light, right? Put in here, the author indicates a section of the single, would be the classical, which would be just a no interference pattern. But of course, it's not true. But he does correctly point out that when a second slit is open, regions would bright become dark and destructive interference. But like I said, it's sort of true if you're just looking at that central maximum area. But yeah, we'd actually have single slit interference patterns in both. And honestly, Brian knows this, but he's just basically dumbing it down a bit, if you will, to make it a little easier to follow, right? So I think that's, if we were to chat, if I was to chat with him, he'd probably be like, yeah, well, a little white lie, basically, right? Just to make it easier for the masses to follow. So yeah, this applet here, if we go back to it, we can switch to electrons. Fire electrons in one by one, I think. While there's electrons going through, and then do this, and controls. It's just basically pause for a sec, see if I can remember how to do this. All right, I must be thinking of a different slide or a different applet or a different video or something. But anyways, here, the point here is, you just fire electrons and it makes an interference pattern. You can even fire, and this is something that physicists have done, you can fire neutrons, makes an interference pattern. You can even fire helium atoms, like helium nucleuses, and it'll make an interference pattern. So it's absolutely experimentally confirmed that particles show wave properties, right? And so, an applet shows a single photon. So it's going to show, okay, my slide is helping me see where it is. Single particles, here we go. Anyways, so send in a single particle of a photon, right? Put the double slit in place and you send this single particle and the applet's going to show like it kind of like going through the two. And, as we do this, see how if one single particle landed there and then one single particle landed there and so on. You just go this and make this go and you just auto repeat here, I guess. And it'll just keep going and it'll gradually fill in an interference pattern, right? And we can switch to like firing in nucleuses of a helium atom as well, and you get that same result, right? So, anyways, yeah. So the applet shows the photon or the particle as some kind of weird, mysterious blob that splits and somehow goes through both slits. And then it's like, well, what really happens? The answer is nobody knows, right? We'll look at the main ideas soon about this, but reality is no one really knows exactly how or why that works. But I'm going to show you lots of stuff to do with it soon. All right, so that's enough for this one. Compton scattering and pair production, just some concept questions to do with it. We're skipping the math work to deal with it. It's a little beyond the scope of the course, and I hope that makes sense. Thanks for watching.